This will be the second lecture in Chapter 4, where we will cover the addition rule and the multiplication rule. Here's a key concept. In this section, we present the addition rule as a tool for finding the probability of A or B, which is the probability that either A occurs or event B occurs, or that they both occur. So, as the word or in the addition rule is associated with the addition of probabilities. Also think the union of sets. So if this is event A and this is event B, then the probability of A and B would be the total shaded area. And we also talk about the multiplication rule used for finding the probability of A and B. And that's the probability that event A occurs and also event B occurs, not just one or the other. So in an event diagram depiction, if this is event A and this is event B, then we're interested in the intersection of the two. Compound event. A compound event is any event combining two or more simple events. The addition rule. So our notation for the addition rule will be the probability of A or B is equal to the probability in a single trial. Event A occurs or event B occurs, or they both occur. The intuitive addition rule. So to find the probability of A or B, add the number of ways event A can occur and the number of ways event B can occur. But add in such a way that every outcome is counted only once. So the probability of A or B is equal to that sum, and then divide that by the total number of outcomes in the sample space. And we have a formula for the addition rule. So the probability of A or B is the sum of the individual probabilities, and then subtract out the probability of A and B. Disjoint events and the addition rule. So disjoint or mutually exclusive is when events A and B cannot occur at the same time. So in a Venn diagram depiction, mutually exclusive events have no overlap. Here's event A, here's event B, and here's the sample space. So for disjoint events, event A, randomly selecting someone for a clinical trial who is male. And event B, randomly selecting someone for a clinical trial who is a female. The selected person cannot be both. And an example of an event that is not disjoint would be event A, randomly selecting someone taking a statistics course, and event B, randomly selecting someone who is a female, because it's possible to be both a female and in a statistics course. The depiction might look like, here is the sample space. This is the sample space consists of students in a stats course. And you might have some division is equal to female students. B is equal to male students. So S is the entire set, and all the female students are definitely within the set of students in the stats course. But if you're a female student, then you're not in the set of male students. Summary. Here is a summary of the key points of the addition rule. To find probability of A or B, first associate the word or with addition. So when you see or, think addition. To find the value of the probability of A or B, add the number of ways A can occur and the number of ways B can occur, but make sure that you don't double count. And we'll see examples of that in the homework. Complementary events in the addition rule. So we use a complement to indicate that event A does not occur. Common sense dictates this principle. We are certain with probability 1 that either an event A occurs or it does not occur. So it follows that the probability of A or A complement is equal to 1. Because events A and A complement must be disjoint, we can use the addition rule to express this principle as follows. The probability of A or A complement, since they're disjoint events, the probability that something either happens or does not happen has to equal 1. And this makes sense from our formula for calculating the probability of the complement of event. Probability of A complement is equal to 1 minus the probability of A, which we talked about in the last lecture. And note, if we were to just simply add P of A to the other side, then we would have probability of A on this side plus probability of A complement equals 1. So here are our rules for complementary events, and you definitely want to memorize this one, because then you can derive the other two. And this one really captures the idea of the complement. So complementary events are necessarily disjoint, and their sum is the total probability of something occurring or not occurring has to be 1. Here's an example. Sleepwalking. Based on a journal article, the probability of randomly selecting someone who has sleepwalked is 0.292, 29.2%. So the probability sleepwalked is equal to 0.292 based on this data from this neurology journal. If a person is randomly selected, find the probability of getting someone who has not sleepwalked. So the probability of not having sleepwalked be, well, 1 minus the probability of having sleepwalked. We're given that probability as 0.292. So 1 minus 0.292 will get us 0.708. Multiplication rule. So our notation, emphasis on and, probability of event A occurs in a first trial and event B occurs in a second trial. And then we have this notation here, probability of B given A. So probability B vertical slash A means probability B happens assuming event A definitely happened. So you go and find out what event A is, and then you see how that would have an influence, if at all, on event B occurring. To find the probability that event A occurs in one trial and event B occurs in another trial, multiply the probability of event A by the probability of event B. But be sure that the probability of event B is found by assuming that event A has already occurred. So, the probability of A and B is the probability of A times the probability of B given A. Independence. So two events, A and B, are independent if the occurrence of one does not affect the probability of the occurrence of the other. Several events are independent if the occurrence of any does not affect the probabilities of the occurrence of the others. So if A and B are not independent, they are said to be dependent. So events are independent if they do not affect the probability of one another. And they are dependent if they do affect the probability of one on the other. Let's say if they do affect the outcome of one another. Look at an example involving screening for drugs. 50 test results from the subjects who use drugs are shown below. Positive test results, 45. Negative test results, 5. For a total of 50 drug users. If 2 of these 50 subjects are randomly selected with replacement, find the probability the first selected person had a positive test result and the second selected person had a negative test result. So with replacement would mean find the probability the first selected person had a positive test result So first selected person has positive test. So if we were to randomly select one person, well, there are 45 positive test results and a total of 50. That's the sample space, sample size. So 45 over 50 would be the probability of selecting someone with a positive test result. Now, if we were to put that person back into the sample size space and then randomly select someone again, it would be possible to select that person again. So on our second trial, we still have 50 people that we can choose from, and the probability of getting someone with a negative result would be 5 out of 50. Now those events will be independent, so we can multiply them together. And here we see that factors of 5 cancel, left with 9 and 10. Your factors of 5 cancel, left with 1 and 10. So 9 over 100, or 0.099% chance. Now, without replacement, let's go back up to here. So the probability of a positive test first person is still going to be 45 over 50. But without replacement, well, then the probability of a negative test, second person, since we're not putting the person that we selected the first time back in, and we're assuming that we selected someone with a positive test, we will then have 5 drug users with negative test results drawn from 49. And then we multiply them together. 45 over 50 times 5 over 49. 5's cancel. Left with a 10 here. 5's cancel here. And we have 9 over 98. So as we see here, the first selection is positive, same probability, 45 out of 50. But then without replacement, we have one less person in our pool, in our sample space. So, but there are still 5 drug users with a negative test result that could be drawn from that sample space. So it would be 5 out of 49, and then we multiply those probabilities together and we get 0.0918.
So in the world of statistics, sampling methods are critically important, and we say sampling with replacement leads to independent events, and that sampling without replacement, it leads to dependent events. A little more complicated. Treating dependent events and independent. So we have the 5% guideline for cumbersome calculations. When sampling without replacement and the sample size is no more than 5% of the size of the population, you can treat the selections as being independent, even though they are technically dependent. So when it's less than 5%. So assume that 3 adults are randomly selected without replacement. So without replacement would mean technically dependent events, but we're talking about 3 adults from the 247,436,830 adults in the United States. So 3 out of 247,436,830 is far less than 5% of U.S. adults. This symbol here means far less than. It's a minuscule proportion of the adults in the U.S. So also assume 10% of adults in the United States use drugs. Find the probability that the 3 selected adults all use drugs. So the probability, we can assume independence. Because the sample size is less than 5% of population. So the probability of randomly selecting 3 drug users would be the probability of randomly selecting a drug user, which would be 1 in 10, times the probability of selecting a drug user, 1 in 10, times the probability of selecting a drug user, 1 in 10. So that would be 1 in 1,000, or 0.001. Or about 0.1%. So we can see that here our solution is calling for using the 5% guideline for cumbersome calculations. Since 3 is clearly no more than 5% of the population of nearly 250 million adults. And so the probability that the first user, or the first adult uses drugs, and the second uses drugs, and the third uses drugs, would be this multiple, the product of their each individual probability of using drugs. So 0.1, this is I used 1/10, that's the same as 0.10. So 0.10 times 0.10 times 0.10. There's a 0.00100 probability that all 3 selected users, adults, use drugs. Redundancy, important application of the multiplication rule. The principle of redundancy is used to increase the reliability of many systems. Our eyes have passive redundancy in the sense that if one of them fails, we can continue to see. An important finding of modern biology is that genes in an organism can often work in place of each other. Engineers often design redundant components so that the whole system will not fail because of the failure of a single component. So example, the Airbus 310, redundancy for better safety. Modern aircraft are now highly reliable, and one design feature contributing to that reliability is the use of redundancy, whereby critical components are duplicated so that if one fails, the other will work. For example, the Airbus 310 twin-engine airliner has 3 independent hydraulic systems. So if any one system fails, full flight control is maintained with another functioning system. For this example, we will assume for a typical flight, the probability of hydraulic system failure is 0.002. If the Airbus 310 were to have one hydraulic system, what is the probability that the aircraft's flight control would work for a flight? And given that the Airbus's 310 actually has 3 independent hydraulic systems, what is the probability that on a typical flight, control can be maintained with a working hydraulic system? Right? Well, A is straightforward. If it was to have one hydraulic system, and we know the probability of failure is 0.02, what is the probability that the aircraft's flight control would work for a given flight? Well, working is the opposite of failure. So probability of not failing that's the complement of failing. So we would know the probability of failing is equal to 1 minus the probability of not failing. Probability of failing is 0.002. And we can do some algebra here and get the probability of not failing is equal to 1 minus 0.02 or 0.998. Right. Now, with 3 independent hydraulic systems, flight control will be maintained if the 3 systems do not all fail. The probability of all 3 hydraulic systems failing is 0.02 times 0.002 times 0.002. And multiply those together, and you get 0.00000008. So when they're independent, that means multiply their probabilities. So the probability, let's go back to the question. So given that there are 3 independent hydraulic systems, what is the probability control can be maintained with a working hydraulic system? That means at least one of them has to survive. So the strategy for B is, what is the probability of not failing? Well, that's 1 minus the probability of failing. And in order for the system to completely fail, all of them would have to fail. All three would have to fail. Since they're all three independent, that would be probability of first failing and second failing and third failing. And since they're independent, we can change these ands into multiplication. So 1 minus probability of first failing times probability of second failing times probability of third failing. And the failure rate is 0.02. So, well, looks like I ran out of room here. Come down to here. So I have 1. Probability of the first failing is 0.002. And the second, the same. And probability of the third failing is the same. And then these numbers multiply together to give us this number, and we subtract, and then we get this would be the probability of at least one hydraulic system not failing. All right. So feel free to read through this on your own. And here's a summary of our addition rule and our multiplication rule. And now here's an example I came up with that is related to this hydraulic problem above. So here is a depiction of the hydraulic systems linking the landing gear of a plane to the control console. A design flaw resulted in these two hydraulic systems, two of them being connected in such a way that a failure in one will make the other one unable to perform its intended role, so that effectively if one fails, the other fails. So what is the probability of the system working if the first hydraulic system, H1, fails? So this one is independent of the other two, but let's assume that it failed for whatever reason on a given flight. Now we have two systems that are actually dependent. So if one fails, then it's 100% probability the other fails. It just won't have enough juice to get the job done. So what is the probability of the system working? In this case, so now we want to see what is the probability if H2 or H3 fails. So now we're adding up the probabilities, because if one or the other fails, or if both fail, then the hydraulic system for the plane won't be able to function. So we add the probabilities of each individual system failing, and then we subtract out the probability of both of them failing. So both of them failing would be an independent event. So if this one fails on its own and this one fails on its own accord, that would be the probability of both of them failing. not of the probability of one of them failing and the system not being able to function. So that's of the multiplication rule we use to find the probability of both of them failing, and then we add up the probability of each of them failing, and then subtract out the probability of both of them failing. That gives us this number here, 0.003996. So then the complement that not the opposite of one or both of them failing would be that neither H2 nor H3 fails. So the complement would be 1 minus this probability, which we calculated above. So the probability that neither this one nor this one fails is 1 minus the addition of their probabilities. So we get 0.996004, which is less than the 0. What did we have for 3 independent systems? 99999999, 8 nines and a 2. So that's less than 0.9999999992. So it's clearly better to have 3 independent systems than to have 2, essentially. So assume that the flaw was fixed and that one of the hydraulic systems failed. So what is the probability of the system working now if H1 failed? So the probability that H2 fails and H3 fails would be 0.02 times 0.02, which would be this number. So then the complement of, or the opposite of H2 and H3 failing will be 1 minus the probability of H2 fails and H3 fails. So 1 minus 0.000004, which is 0.999996. So see the improvement. It's definitely safer with 3 independent systems. When these were dependent, so that a failure in one guaranteed a failure in the other, we had a 0.996004. So 0.996004, definitely less than 0.999996. So thankfully the engineers and mechanics caught that and fixed that flaw. Alright, that concludes this lecture.